Okay, so I'm going to make at least one video. I don't know if I'm going to make it into 2 videos. It might be too long. On the homework that you are doing today. That is section 2.6. So starting with problem 5, because that was what was requested, I'm going to do 5 and 7 of practice set 1. And then I think it's 3, 5, 7, and 9 on practice set 2. So I'm going to guess that the issue is graphing calculator versus Desmos. So I'm going to try to show you both, but I'm going to recommend the graphing calculator because it can do everything. All right, so starting with number 5. So it says a local print shop sells yard signs for realtors in bundles of 50 signs. The profit margins for each bundle are shown below. Assume the behavior is quadratic for up to 800 signs, which after I did this, I realized that 800 is kind of where it, the quadratic, the parabola turns. This is around 800 right here. So that's why it's saying that, because it wouldn't continue with profit, right? It would decrease, which would not represent a good model in the context of this word problem. All right, so I'm going to try to show you with my graphing calculator hovering over my iPad, so bear with me. Okay, where are we? Here we are. Okay, so I've put the numbers in, and now I'm going to do a quadratic. So it is stat calc down to 5 quadratic, and then you always want to put it in y equals, and I always do it this way. Okay, so there's my question, or that's what I put in answer blank A, and negative 6e to the negative 4 is times 10 to the negative 4. The e is exponent on the 10. It's scientific notation. So you're basically moving the decimal 4 places to the left, which just means you're putting 3 zeros in front of the 6. So it's negative 0.0006 x squared plus 0.958x minus 37. Okay, and that's what I wrote on the homework, which I have right here. All right, so that's what I wrote. All right, so now if you wanted to fill in the chart, you're just going to your table. So we're starting at 50, so let's do it like this. Let's go down to ask. And then second table, and we're just plugging in the numbers. So 50, I can't really see what I'm doing, so I'm gonna peek 100, 150, and 200. All right, so that's what you would put in the y hat column, which just means, y hat is just a statistics symbol for the regression equation, whether it's linear regression, quadratic regression, whatever. So those are your predicted values, right? When we did residuals, predicted values right here. So the next column, your calculator can do this for you. You don't have to actually subtract 9.4 from 15 to get that next column, right? 9.4 would go here from 15. You don't have to do that by hand. So I'm going to show you how you can do it. So stat, edit. Okay, so that's the table. You just go up to 3 and hit enter so that whatever you type here is going to register there. So second list, number 7. And that's those numbers. Okay, so those are your residuals. All right, if you wanted to see the graph, this is our equation, put it in automatically. If you want to see the scatter plot, you turn it on, it's on scatter plot. So we do zoom, and then you just arrow down or just hit the number 9. I just hit the number 9. And you'll see the scatter plot and the function, the regression function going through the scatter plot. That's kind of how on, I think it was number 7, I picked the best fit graph. You will not have to do that on a quiz or a test for me. All All right, so now if you want to see the residual graph, because that's what question B actually asks, right? Question B is asking based on the residual plots. So how do we see that? So we're going to go back up here. We're going to go back to our screen. I just hit enter. I'm hitting enter. I'm going to go down to Y2, and I'm going to make it say residuals. I want them to plot, and I probably could put Y3 since I already put my residuals in here, but I just always do it like this. Second list, option 7. And I think you guys, the calculators that you use in my class, it would be option 9, but just look at your screen. And then zoom 9 again. All right, that's just what's in Y equals. All right, so this is your residual plot. And as you can see, I put, you know, it's randomly scattered, so it's a good model. And I just always say, because, you know, the points are on both sides of the x-axis with no pattern showing. And that's all there is to that one. All right, let's go to number 7. Whoops, that's not the right screen. Hold on. Okay, number 7. All right, so for this one, all right, this one is interesting because it doesn't tell you if you need to change your x values. And if you were to use the numbers, the actual numbers in the table, when you do L1, L2, you don't want to use those numbers. You don't want to use 2005 and so on, because we're at part B says explain the meaning of the y-intercept. And you know, the y-intercept is when your x values are 0. So if you put in the numbers 2005, 6, 7, 8, etc., the y-intercept would be in the year 0, literally the year 0. So that wouldn't make sense. Your y-intercept would be some crazy number. So you want to change it. That's why this problem was a little weird. In her answer key that I'm sure you've looked at if you've done this problem, she used t equals 0 for 2004. I don't know why, it's just random. I probably would have said, you know, t equals 5 for that number and then t equals 6. But there's, you know, there's no wrong way to do it. So I just did it the same way as the answer key, since I've already posted the answer key for you guys to look at. So if we said t equals 0 represents 2004, then this would be t equals 1, 2, 3, 4, 5, 6, 7, and 8. All right, so when you get, okay, and now I guess I need to do this one because, I'm gonna do it off to the side real quick. I'm clearing my memory because of the last problem I just did. And now I'm quickly putting 1, 2, 3, 4, 5, 6, 7, and 8 in Y1. And then let me go ahead and just let you see what I'm doing. And then so I'm putting those numbers in right here. So I'm just gonna have to keep it, you looking at it like that, and then I'm looking off to the side. 10.01, 10.86, 11.55, 11.18, 10.6, 10.69, 11.07, and 11.82. All right, so now I want to see, because it definitely does not tell us to use cubic. It says determine the type of regression that best fits the data. All right, so the way we do this is we look at the scatter plot. So first, you just go second y equals and look at your scatter plot. Now, hopefully I don't have anything in y equals. If I did, I'd just hit clear because I didn't clear my memory. Maybe I did, I can't remember. Anyway, so I'm ready to look at the scatter plot. So zoom 9. Now look at that scatter plot. That clearly looks cubic, doesn't it? That's what it was. I never even checked anything else because it just looked so clearly cubic, right? It's going up, then down, then up again. That's cubic. So stat calc number 6 is cubic. And storing the equation in y1. All right, so that's where that equation comes from. That's where all those numbers come from. Okay. Okay, so there's that. And then we interpret the y-intercept, right? The y-intercept would be in the year 2004. The bottled water producers' revenue in billions of US dollars was 7.9. So $7.906 billion was the water bottle producers' revenue. And then it says using the residual plot. So let's look at that. Okay, so now we're going to go second y equals and hit enter to get into the screen. And then instead of using our scatter plot points, I want to see the residuals. So I'm going to do second list option 7. And then you just hit zoom 9. Right, there's my residuals. So we see that it is randomly scattered, fairly equal points on both sides of the x-axis. No pattern is always what you want for residual plots. All right, so we know that that is good, and that's what I wrote. Using the residual plot for the regression model, do the residuals follow a definite pattern, or are they randomly scattered? So randomly scattered, and I just drew it here. And then it says find a linear model. All right, which would, of course, would just be stat calc 4, and then store that one. So there's that equation. And then it says, based on your findings, which model best fits or makes the most sense of the data? So if we were going to look at the residuals of this one, it's set right. So now it's just, let's make sure it's in y equals. Yep. So zoom 9. Okay, we see a pattern. So that's not a good model. So based on everything are being taught about residuals, you wouldn't say the linear model is a good fit. However, because of the context of this particular problem, it's saying from the year 2005 to the year 2012, the revenue in billions of dollars in the US for the sales of water bottles, it wouldn't really make sense for, the cubic graph. Where did I write it? I guess I wrote it on that other screen. Let me go back to that. On this screen. Oh, that was in my last video. That didn't work out. So anyway, since cubic, does this, so we're talking about this area right here. All right, so what I was about to show you on my answer key, let me go back to. So that's this part. All right, so I was about to say cubic, but it's not. I was about to say exponential, but it's the far right part of the cubic function is going up rapidly, because that's what a cubic does on the far right end. It's a rapid increase. And linear is a slow increase. So when you're thinking about the context, if you think about, the economy and the demand, this one makes more sense, because it's not like all of a sudden it's going to hit the year 2015 and like everybody's going to buy 10 million bottles of water all at the same time. It's not like that. So that's why they're saying think about the context. So that's all that problem is talking about. All right, let's go back. All right, so that's 7. Okay, in set 2, the request was problems 3. And let's look at that one. Problem 3 is not a whole lot of work, so let's read it. So it says the scatter plot displays a set of data along with its least squares regression line. Don't worry about that. That is just the linear regression line. I guess she used to teach stats, or maybe she still does, because that's what you do in stats. It's just the same thing as linear regression, so don't freak out about that. All right, so consider removing the outlier to -7, which would most likely be that. That would be the outlier, right? Because, if we've got a bunch of data, this is closest to 0, so that's got to be the outlier they're talking about. Plus, it's kind of far away from the regression line. So it says, consider removing that point. I don't know if y'all remember, or even if you did this in Math 1, but back in the day when I taught Algebra 1, occasionally to teach them regression lines, I made them do it by hand. So if you had a bunch of points you plotted on graph paper and then used a ruler, you would try to draw a line of best fit that kind of modeled the pattern of those points. So this is basically saying, what would our new line look like? And I'm going to use my ruler tool. I don't know if you can see the ruler tool on this recording, but basically you're ignoring that point that I crossed out. So this would probably be a good pattern of your new line, something like that, right? So it says consider removing the outlier and calculate a new regression line. So we'll say this is our new regression line. And we're not doing any math, we're just kind of approximating. It says the slope of the regression line would increase. Well, getting steeper in the negative direction is actually decreasing. So you would say false, steeper, negatively is, slope is decreasing. Right? If you're comparing the red line to the blue line, right? The blue line's slope is negative, but it's less steep. So you might say that's the slope of -1. And then the one that's red might be -2. I don't know. So that number is decreasing. All right. The y-intercept of the regression line would increase. That's true because you see, whoops, I can't spell. True. Because we see that the blue one's y-intercept was about there. The red one's was higher up on the y-axis. That's all. You don't even have to give a reason. That's it. All right, number 5. All right, on number 5, it says your agriculture club plants a different bean variety each week for 11 weeks. 2 weeks after the last bean was planted, I think that's supposed to be spelled B-E-A-N, but whatever. The plants have heights shown in the table and in the graph. The behavior of the data has an upward trend. Can you determine the best fitting function model? All right, so we don't actually have to put that in our calculator just to figure out the best fitting function model. I mean, we're looking at the scatter plot, so it could be linear, it could be exponential. So part A says, go ahead and calculate the linear regression and the exponential regression line. So if I put all those numbers in and did stat calc 4, right? This one would be stat calc 4. This would be stat calc, and what is it? Turn it on, stat calc 9. No, 0. Number 0, right after 9. All right, and you get, we'll just put the little hat, 2.164x minus 3.691 is what I got. After putting all that data in L1, right, you do this one in L1, this one in L2, and then stat calc 4 for linear, and then stat calc 0 for exponential. Much easier than Desmos for this, I think. And your base is 1.233 raised to the x. So it says, analyze the residual plot for each regression equation and then explain your findings. All right, so for me, I didn't write all the things she wrote. I just looked at the residual plot for my linear one, and I drew a little pattern so that I could talk about it. So here's my horizontal line, and then the scatter plot was like, we had, nothing exactly like this, but we had some points above and then some points below, but it kind of looked like a pattern, right? It was increasing on both ends. So I said that a linear model is, I'm just going to use the word bad because it shows a pattern. Pattern with the residuals. All right, and then with the exponential, I saw that the pattern was kind of evenly spaced on both sides. No pattern showing. So it was a good, exponential is a good model because no pattern, and it was randomly scattered. But evenly scattered really is what I always kind of think about. Evenly scattered on both sides of the x-axis. That means the regression equation or graph of the regression kind of goes through those points as best as it can. Best fit. So which regression best fits? I said exponential, and that was it. You can read the additional stuff she said, but I don't think you need to. And that's it for number 5. So let's look at number 7. Okay, a jet ski's average speed, y, in knots for several engine speeds, x, in hundreds of revolutions per minute, RPMs, are shown below. Use the data to determine a polynomial of best fit. How did you determine your model? All right, so I'm going to do this one. It might be a little bit boring for you to watch, but I'm going to do it anyway. All right, so first, clear the memory. Second, plus sign 7, 1, 2. All right, so then, oops, stat, edit. All right, 8, 11. Okay, so 8, 11, 14, 17, 19, and 22.5. I'm trying to make sure I'm showing you guys what I'm doing. And then in the Y column, or the L2 is 8.97, 14.18, 19.62, 26.05, 31.29, and 43.13. All right, so we don't know what is the best fit model. So first let's look at the scatter plot. So second y equals, hit enter to turn it on. And looking at your screen, it's on scatter plot, L1, L2. So we just graph it now. So zoom 9. All right, well that didn't help, did it? It just shows me it could be linear, it could be part of a quadratic, it could be part of a cubic, it could be exponential. So, of course, if you took Math 4, you know about your correlation coefficients and turning your diagnostics on and comparing your R and R squareds. We're not doing that at all in this course, as the video said. So what we're doing is we're just going to look at how well each regression fits these points, and then we're going to look at the the residuals. All right, so first we have to generate, I did linear first. So I went stat, calc, 4, and I put the linear regression in Y1. All right, I didn't necessarily write it down on my paper. I just put it in there, and then that means it's in Y1. So I'm going to look at my scatter plot. So zoom 9. Whoops, did something wrong. Zoom 9. All right, so this is showing the linear function going through the scatter plot. All right, that's a pretty good fit. Let's check out the residuals. So second y equals, hit enter. Now I'm going to change that to residuals. Second list 7. Now zoom 9. All right, so I see it is not the greatest fit because this is my residuals. It looks like a parabola. So it's making a pattern, so you know it's not linear. All right, so I go to my y equals, and I'm going to clear that out. And then I've still got the data in L1, L2, so I'm doing stat calc quadratic. Do it again. Alpha trace for y1. Okay, so it's in y1. If I want to see how close it fits the data, I need to change it back from residuals to L2. So L2 is second 2, and it says L2. And then zoom 9. All right, so now we're looking at a quadratic going through the scatter plots. That looks pretty good. All right, So now let's check out the residuals. Second, y equals, go down to L2 and change it to residuals. Second, stat, option 7. All right, and then zoom 9. All right, so this is looking, to me, this looks like a pattern, kind of up, down, and back up. But at the same time, you could say, well, it looks pretty scattered. I mean, 3 points above, 3 points below. So, you know, I'd maybe say, well, maybe quadratic's good. Now let's check out cubic. So I'm going to delete that one and do stat calc 5. Oops, 5. Alpha, trace, enter. Let's just look at the residual since I've already got it in there. So zoom 9. All right, that one looks a little bit better, more scattered. Now let's see what it looks like going through the points. So back to L2 and then zoom 9. So this one looks like it's fitting even better. Look at how that turned and went right through every single point. So to me, it looks like cubic is a little bit better. Now it said polynomial function of best fit, so I'm not going to check exponential. All right, so looking at what I wrote when I worked this out, I just jotted those two down and I said cubic was better, and I looked at each scatter plot and looked at the residuals. All right, so now go back to this. All right, so the next thing is B. All right, use your model. So that was your cubic, right? The cubic was the 0.00495 x cubed. Well, it was minus 0.1519 x squared plus 3.274x minus 10.037. Okay, so we're using this model to estimate the average speed for the jet ski. So that's finding our y when the engine speed, so x is 2,500 RPMs. Well, look at our x's. They're not in the hundreds. So we have to remember it said that this is 800, 1100, 1400. So that means x is 25. So we can show the notation like this, like plugging in a 25. And of course in our calculator, let me go back to that. In our calculator, right, we've still got our cubic in there. And you can scroll across to make sure it says to the third power, x to the third. It does. And now we're just gonna, there's two ways to do this. I don't know if you saw this, but of course we can always do second window and put 25, which is perfectly fine, and then go to your table. But I've been doing this alpha y1, and then it's just kind of like function notation. So 25. And you don't have to close the parentheses, but that gives you your answer. That's 54 knots. I'm not sure why I wrote 22 knots. Maybe that was what she had. Let me check. Yeah, her answer was 0.22, but mine was 0.24. All right, so that's fine. That just is based on if you used the the equation that you wrote down, right? Those rounded numbers, or did you use the whole thing? So I think on one of the prior examples, she had used just those, which I would never do. So you always want to use the exact values. All right, so that's answer B. And then it says, what engine speed will produce a jet ski speed of 20 knots? All right, so in Y1, we've got our best fit cubic. So then in Y2, you're trying to figure out what X will be when Y is 20, right? So we graph that, and it happens to be going right through it. So we're going to calculate second, trace, calculate the intersection. So that's option 5. Enter, enter, enter. And that is your answer. 14.199 RPMs would be 1,420 RPMs. Okay. All right, the next one. The last one of your homework. All right, so this one talks about number of hours you work and how many your total tips. And this one is clearly, at first I was looking at it as an outlier, and then I read on part C, her father gave her a $100 tip. So if we take that 100 off, basically it's asking how is that going to be different from our regression equation. All right, so I'm just going to show you my answer key first. It's just easier that way, because I can just talk about it and then show you with my calculator what I need to do, what you would need to do. All right, so I put all that in, including this number and I did stat calc 4 for linear, and I looked at the scatter plot to see if it fit, and I said it wasn't a great fit, and then I did quadratic, and I noticed it wasn't a great fit with the points, and cubic was okay. I looked at the residuals. Exponential was okay. And I went ahead and picked exponential because I think when I graphed the exponential regression through these scatter plot points, it was better than cubic. So that was the equation I decided to go on. All right, and then it said find a linear regression model. What do you notice about Y1? So I did that linear again and wrote it down. And when you plug 1 in, you get negative 0.75, meaning, she got negative tips on a day she worked 1 hour. That doesn't make any sense. All right, so then it says, Shelby said that her father gave her a $100 tip on the day that she worked for 0.75 hours. So if you just change that by taking off the $100, how does the regression equation change? So I compared my one that I thought was best and the linear one, since those were the two we were looking at, and just ignore my original. I had put in the point wrong. I had taken the whole point out at first because I didn't read closely. Be aware, it's important to read closely. So this is your exponential regression, and looking at the scatter plot, it was much better fit. Not a hugely better, but better. And then, okay, so part D. This was the part I thought, let me go ahead and make sure I explain this to you guys. So on my better fit exponential function, I drew my scatter plot, which was these points, but not 148, but just 48.75. And then my exponential regression, I drew that in green. My original linear regression, that gave me a negative money here, and taking out the 100, it gave me an even bigger negative. That would be in purple. And so it was saying, can you calculate a better linear model than the one in purple by adjusting the y-intercept to 0, 0 using that point? So what that means is this scatter plot point, instead of using all the scatter plot points and generating a linear regression of best fit considering all the points, use the origin and that point and get a line. So I actually did y2 minus y1 over x2 minus x1, and you get this linear regression in orange, looking at my graph. Okay, so now to answer the question, it says, can you calculate a better linear model? Well, yes, it's better, but explain. So I said, for the context of this problem, I would think before I even typed these in, I thought this would be linear because, the more hours you work, the more tips you're going to make. Doesn't that make sense? More people you're waiting on, you're going to get more tips. So really, a linear model is better than exponential because what does exponential do? It goes up really fast after a certain period of time. So it was saying, or basically you can say or analyze that after 6.5 hours, the better fit exponential isn't really a good fit anymore because it's going up really fast. And you want it to be more linear, slower growth. Linear is slower growth than exponential. So that's all you had to say. I know that might have seemed really confusing trying to follow what she wrote. So I hope that helps. All right, email me if you have other questions, and I will see you on Monday.